Hello everyone, welcome to Finetune any LLM course. In this video, we are going to see how you can fine-tune any LLM to follow your instruction by using TRL's SFT trainer. This video will be all you need for you to adapt your LLM to any custom use case of your choice. So stay till the end to know how you can fine-tune any LLM for your custom use cases. In this video, I'm gonna take up the latest released model from Hugging Face, which is Small LM2, 135 million model, and I'm gonna fine-tune it in Google Colab itself on Alpaca dataset. Let's start with the installation. What are the installations you require? Transformers, TRL, PEFT, which is parameter efficient fine-tuning, in which it has the capability to provide adapters, for which here we are going to use LoRa adapter, but there are many varieties of adapter. If you want a video on the types of adapters, please let me know in the comments. I'll try to make a video on the different adapters which are available and when you can use which and which is the better one. We'll see everything in detail. And then we have accelerate for efficient GPU computation, datasets to manipulate the dataset. All can be done with the help of datasets. And then bits and bytes for us to load the model in a quantized manner in 4-bit, because that will allow us to train the model. So the installation is going on as well as the model will be loaded. Let me see you after that. So right now you can see the model is loaded from Hugging Face, and they have apparently used the Llama code itself, where Llama model is there. There is a LM head, but the vocab size is something very weird. I haven't seen a vocab size like this. Probably to keep the size of the model lower, they changed it. Apparently, I'm not sure. But the vocab size is 49,152. You can see here, right? 49,152 embedding tokens are there. And the embedding dimension is 576. That is also kind of a weird number. I haven't seen that before. Again, that is because, it is a very small model, very, very small model, So yeah, this is a good model. There is no doubt in that. Now let's see about the input. There is torch, load dataset to load the dataset from hub, dataset class to have dataset functionalities, LoRa config to specify configuration for LoRa, prepare model for K-bit training to be enabled for making sure that the model is ready for quantized training, get PEF model basically to attach the LoRa adapters based on the PEF LoRa config you have created to the model, small LM2, and then from transformers, auto model for causal LM to get the model, auto tokenizer to get the tokenizer, training arguments to set the training arguments, and bits and bytes config to load the model in a quantized manner. SFT trainer, which is basically the advanced PyTorch trainer, which they have written behind for supervised fine tuning, which is none other than the instruction tuning. Accelerator, so that when you do for multiple GPUs, right, this will be very important. And then OS for OS related functionalities. These are some standard imports, and here is the configuration. Okay, let's come to the configuration when we go through the code. Okay, so here you can see the function is train and save model, where first I'm calling create trainer. Where is the create trainer? Here it is, where first I'm loading the model and tokenizer, and here it is load model tokenizer. Here if you see, first we call auto model for causal LM.from pretrain, where we provide the model checkpoint, load in 4-bit. Here it is set to true. You can set whatever you want. Device map is set to auto, so that if CUDA is available, that will be used. If not, it will use CPU. Basically you can't CUDA device map is to set the device number in CUDA itself. If you are using multiple GPUs, some might be 0, some might be 1, some layers actually, it will be initialized at GPU 0, GPU 1. So for that you need device map, and then torch dtype to set the float the data type of the model, basically the tensors in the model. And here model config use cache is set to false, because we are training and we don't need KV caching while training, so that is there. And pre-training TP, which is to ensure that the pre-training performance is replicated. And here we call prepare model for k-bit training so that it is ready for, training with the quantized bit rather than the 32-bit in which it is originally in. And now we'll see if we need to use LoRa. Now, if you're wondering, the config is there here. Okay, load info bit is true. Device map is obtained by using accelerator. Trust remote code is set to true. Use LoRa is set to true. And here is the LoRa configuration. For people who don't know how LoRa works, I would recommend you all to watch the video which is already there in the channel for LoRa. The link will be in the description. Please watch that. But I'll give a gist right now on what is LoRa and how it works. So let me take yellow. Usually, if you have a layer like this, okay, the formula would be Wx plus B. And here, what happens in LoRa is, basically, here there will be a dimension which is 1000, let's say. The output dimension also will be 1000. This is how it works with linear layers, okay? Here what they'll do is, in LoRa, along with this, they'll add something known as adapter, okay? And this adapter will go something like this, okay? There will be A, which will be of 1000 cross 8. We call this 1000 to be D. So it will be D cross R. This 8 is rank, okay? LoRa rank. And so it will be D cross R and then R cross D, okay? These matrices are known as weight decomposition matrices. Weight decomposition matrices. And researchers have found that with these matrices, these are rank matrices which are created. These are more than enough to get the performance. And also here, if you see why this came is, first, they are oversaturated. There is a good name for it. I forgot the name. The performance is oversaturated, to some extent. That bigger number for attention is not required. That is what said, that big of a dimension is not required for attention. That is what is said in the paper. That is one. Actually, there are some findings that, LoRa has better results than normal fine tuning, which is not LoRa. Okay. And then second one is you reduce computation while training. Okay. Not while inferencing, but while training. How is that? Here if you see, it was 1000 to 1000, right? So basically what happens, it will be a 1000 cross 1000, which is 30 and then 30. So it is 10 lakh, 10 crore, no, 10 lakhs, yeah. It is 10 lakh params, let's say, okay? It is 10 lakh params here, but it will become something like this. 1000 into 8 plus 1000 into 8. Considering your LoRa rank is 8. So for example, if it is 16 here, it will be 16. Okay. So it will be 16,000 plus 60,000, which is 32,000. Here you can see how drastic of a difference is here. Even if you do this right, the performance either will be equal or very negligible performance, which you won't even notice, or very negligible increase in performance. Which means, effectively LoRa is directly usable, which is not an issue. And one of the biggest advantages of LoRa is catastrophic forgetting is an issue which is stopped. Okay. Because, while you adapt the LoRa adapters, right? Basically what happens is the original layers which were here for adding, right? These layers will be frozen. So that knowledge is still there. And these adapters get adapted to the use case. Okay, so that is what is LoRa adapter. If you want more details on how it works, what are the advantages, please check the channel video, which is already there. The link will be in the description. Okay, thank you. Now let's resume with the training and I'll explain the parameters. Okay, so in the LoRa configuration, which is here, let me close this actually. Yeah. It is gone. So here the LoRa rank is basically 16, where I said 8, right? So there will be replaced at 16. And LoRa alpha is a scaling parameter where your weights will be divided by this number. And here it is 16, that is to normalize. And then LoRa dropout, dropout in the LoRa layers, it is 0.05. Bias is set to none. What is the task type? It is causal language modeling here. And the target model is a very important parameter, which is here Q projection and V projection. How you need to get that? First, get your model, print that, and here in attention, the paper has been said that, in LoRa paper that, if you do LoRa for Q query and value, that is more than enough. That is what they are saying. But there is also another paper which is saying, like, if you do for all these modules, Q proj, K proj, V proj, O proj, get projection, up projection, down projection, every layer, right? It will drastically improve your performance. That is what that paper says. But the original paper says you can be having very good ample amount of performance with the help of Q proj and V proj itself. So I'm sticking on to that. Okay. So that is my LoRa configuration. Here you can see that is what is provided here. LoRa rank, LoRa alpha, LoRa dropout, bias, task type, target modules. All of these are provided. Now the LoRa configuration is set. Now I'll call a getPef model, which will basically take the model as well as LoRa config, and then it will attach the adapters based on this config to the model. Okay. Now my model is updated. Here you can see if I'm using LoRa, I'm just printing the trainable parameters so that you get a log, how much trainable parameters. For example, in this training, right, the whole parameters for training was 13 crore 54 lakhs 36,608 parameters. But we are training only 9 lakh parameters, okay, which is just 0.68% of the whole model. So that's why it is there. If you want, you can just take it off. That is not an issue. Okay. And here, why I kept it in an if condition, I could have just provided it separately. Why I kept it is because in this SFT trainer, you need to provide the following things: your model, your data set. We'll see the data set preparation later. Basically, if you see here, self.data is equal to data is called. Okay. Self.LoRa config, we already have the LoRa config here. Here you can see LoRa config is created in prepare LoRa model, which was already called when we called the load model in tokenizer function. Dataset text field, it is from the configuration where we need to say what is the training column name. Let me search for it. Here you can see training column name is text. In the column text, the data will be there basically. And then arguments, you need to provide your training arguments, which is there in the set train arguments function. Okay, let me explain the arguments now. Output directory where you want to save your output per device train batch size. So let's say you have 10 GPUs. Okay, in each GPU, what is the batch size you want to process? Let's say it is 16. So effectively your batch size will become 160. Okay. Gradient accumulation steps is for how many forward steps do you want to accumulate your gradient and then do a back propagation. For example, let's say my batch size is 2, my gradient accumulation steps is 4, I'm running it in 1 GPU. Okay. So after seeing 8 samples, not 8 samples, 4 steps, 2 batch size, which is 16 samples. Okay. So 8 steps effectively, which is 16 samples. After that 16 samples only, my back propagation will happen. That is why gradient accumulation steps is there. And then optimizer, what is the optimizer I want to use? Here we would have used a paged AdamW optimizer, which is a variant of AdamW, especially created for models which is trained for quantized manner. So right now we are using a quantized model, right? Here you could have seen we would have used load and 4-bit to true. This method is known as QLoRa. Okay, you are using LoRa on a quantized model, so it is becoming a QLoRa method. And here I've provided the learning rate. We all know what is learning rate. Learning rate scheduler, it is linear, cosine. How you want to update your learning rate. There is reduce, LR, plateau, many things, everything has a logic to it. And based on that logic, your learning rate will be updated, which will basically impact your training indirectly. And then save strategy, how I want to save. Do I want it to save by epochs or steps? At how many steps I want to see the logs, which is training loss, validation loss, whatever you want. That is logging steps. How many number of epochs I want to train, and max steps. Like if I have a large amount of data set and I'm just doing a percentage of training, I want to train it only for this much number of steps. Okay, so at that time you can use this. This is usually very useful when you do pre-training, but fine-tuning not that much, because you yourself will have very less amount of data. And then FP16 is set to true because this GPU support mixed precision training. So I have set that to true. Push to hub is set to true. Again, if you're wondering, the parameters are here. Training batch size for one step, it is 24. Gradient accumulation steps is 8. Now you can see why I quantized, right? So effectively, if you see 24 and then 8, if you multiply 24 cross 8, it is going to be 240, 20, 220, 216, 198, I'm not sure, 198 or 120, 192, if I'm not wrong. Let me check. Yep, it is 192. So basically, after 192 samples only, my how can I say, my back propagation will happen here. And then page random W optimizer is an optimizer specially created for quantized, like I have said already. My learning rate is 2e minus 5, which is a standard learning rate for LLMs actually right now while fine tuning. Learning rate scheduler I have set to cosine. You can try linear as well, that is your wish. And then save strategy, I wanted to save it as at epochs. Logging steps, I want to see in my training loss at every 20 steps. I want to train for one epoch. Max steps, I've provided it. If you want, like you can uncomment there. And then FP16 is set to true. Push to hub is also set to true. And I already said the training column name as well. That is the parameters here. And along with these, there are two other parameters. One is Finetuning, where Finetuning is a paper actually which was released sometime before, where that said, like, if you add some noise to your embedding to some extent, it will actually improve your performance and make the model robust. That is what the paper said. And the standard value which was set in the paper was 5. So I'm just using 5. And the max length here, if you see, I've set to 256. I want to train it for 256 tokens only. Because again, collab GPU, not that good. Report 2 is tensor board. By default, it would be 1 dB. So make sure that you provide that, or else it will ask you an API key for 1 dB. Okay. So now these are my arguments. Already we have provided our model data. If not using LoRa config, no LoRa config will be provided. If you are using LoRa config is provided. Training column name, training arguments, tokenizer, which we obtain by calling the load model tokenizer. Packing, basically what it means is, let's say you have a 10 samples and each of these are 128, but you set to 256. So what this logic will do is, it will try to combine sequences with a separated token, such that, instead of training for 10 steps, you will train it in 5 steps, like that. Okay. So I've just set to false. And then max sequence length, already I've provided it to be 256. So now create trainer is done. Now I'll call the trainer, and then I'll save the model in my output directory, and also I'll save my tokenizer in the output directory as well. Here I'm using a dataset which is known as alpaca dataset, a very old dataset. Okay, old but gold, easy for us to understand actually. So what you need to do is just take the dataset. If you want, you can work with the dataset directly. For beginning stuff, I think pandas is more easier because we are more well versed with pandas. So what you can do is just call data and then make it to pandas. Take the data df, okay, and then out of data df, we are just taking 3 columns, which is input, instruction, and output. Okay, we are applying something on that. That is the apply function, where we are applying a lambda function by combining everything into a single prompt. Okay, so basically what it will be done is, like, the instruction, input, output will be combined here, and then will be stored in text. This is what we are going to pre-train. Now we are using the dataset class to create a Hugging Face dataset by calling the from pandas function, which will convert a pandas data frame into a Hugging Face dataset. That is data. The data is written here, and we have already got that here. Okay. Now I am calling my train SFT class, which will take the data as well as config. If you are wondering what is the config is this one. Okay. And when I call the train and save model, it will go for this training loop, which took me around 31 minutes. It ended up in a training loss of 2.64. not as much as I expected it to be. I expected it to come around 1.7 or 1.8. But, I quantized a 135 million parameter. What can I expect? That to 4-bit. But what you can do as an exercise is do these. Okay. Maybe you can all try it out and let me know in the comment section. First, take out the load in 4-bit true, make it to false and train it in its 16-bit itself. It will be loadable. Okay. But what you need to do is change the batch size and all. Batch size, gradient accumulation steps, change it so that it is loadable in Google Colab. That is number 1. And number 2, when you do that, so see the performance and then compare it with providing the target modules with all these values. Okay. Q projection, K projection, V projection, O projection, gap projection, up projection, down projection. So the person who comes up with this experimentation output for the first will be getting a shout out in the next video. Okay. So right now I have like I said, trained it and I uploaded it in my hub where my output directory was small LM2 alpaca. So it is there. Okay. I dropped my phone in water. What should I do? That is what I asked. Actually, I thought it will do some random shit, but it expected, I dropped in water, what I need to do. It just ignored my phone and said, what I need to do, since I fell into water. It is coherent. It is very, very much workable, but needs a lot of training. You can fine tune any of your LLM in this way. But make sure that, you try it with different logics. And also you can try with 350 million, same logic, quantized LoRa with these 2 target module alone, but 350 million so that you will get a better response. Okay. So let me know if you all did any experimentation like this in the comment section. But this is how you fine tune for any task. This is how you'll fine tune your LLM. And I hope you like this video. If you like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon so that you will get notification. I'm uploading almost on a daily basis. I'll see you all in the next video. Until then, if you have any comments, let me know in the comment section. Happy learning.